Welcome to the 10th video of Introduction to Quantum Field Theory. This video will cover the Euler-Lagrange equation. Quantum field theory uses the Lagrangian formalism of mechanics extensively, so before delving into the equation and what it is, we must cover some preliminary facts. We will deal a lot with objects called functionals. So if you have a function, then a function is just some object little f that will, little f that will send some value x to y, and x and y are scalars. So x, y are scalars. This represents a scalar, like scalars. So like an example would be R or C. And this is written as f of x equals y. Now this is some pretty basic stuff, so it seems a little obvious. Why are we talking about it? Well, a functional is similar. So a functional is some object big F that will map from a function onto a scalar, where again x and y are scalars. This is written similarly, except you have capital F and then square bracket little f of x, which typically is rewritten like this. Little f equals y. Even though the function here depends on a scalar, it's typically omitted and you just write the function in the bracket. So just as a function takes a scalar and maps it to another scalar, a functional maps a function to a scalar. So if you have tons of different functions, then you have different number values that you can associate with them. So say we want to go between 2 points. Let's call one A and let's call one B. This is point A, this is point B. Say we want to go to these in the most efficient way possible. So you can imagine you get a path that goes like this, got a path that goes like that, and maybe a path that goes like this. And typically call this path Q of t, and we say it depends on time. Q of t, this will be 2, this will be 1, then Q3 of t. And of course they're going in this direction. So say we want to find the most efficient way. Well, there exist 3 paths. So we must assign 3 numbers, because we need a number associated with each path in order to compare them. And so we need a functional, because these trajectories are functions. And so we're mapping a function to a number. So for the first one, you can have Q1, which I'm just going to write without the t, Q2 and Q3. Well, these will map to what I will write with a big S, Q1. S Q2, big S Q3. And so this big S, this functional, is going to take each individual path and assign it some number that tells basically what its efficiency is. So we call this the action. So S of Q of T is the action. And technically it's the action functional. The most efficient path is the one that extremizes the action. What that means is the most efficient path is the most efficient path is one where is Q of T such that a small change in the functional of that path, which is equal to the definition of this little change. This is just the differential of a functional. So if you have Q of T plus some small perturbation, then minus S, which is just the original, then you want this to be equal to 0. So the most efficient path is the one where if you deviate from the path just a little bit, so that's what this represents. This represents deviating from the path just a little bit. Then the difference between the path with the deviation and the path without the deviation is 0. So you can imagine if this right here is the most efficient path, and I take a deviation like this, and it's like just infinitely close at some points, and it deviates just a little bit, but it's infinitely close, and call this epsilon of T, then this little thing that will exist at different points is infinitely far away. Then if I consider the functional of this path, then it gives me the same functional as just the path by itself, which tells me that trying to deviate away from it it's not going to work because, it's not going to change anything. So deviating a little bit doesn't change anything. And that's what this means. So, going to first, we've talked about this before, but just recall the differential. For a function, the differential of a function is f, where you have this and you add an infinitely small value, then this say approximately equal to f of x plus epsilon, the small change, and then how much f changes in the direction. So f changes in the direction of x. If we perturb it slightly, then the amount that it's been perturbed times the rate of change in that particular direction gives you what the total function is. And this works for functionals in the same way. You have this, you have the functional, which has some, let's call it f of x plus some perturbation, e of x. Then this is going to be equal to f of f plus epsilon times the change of f in the direction of, of f, yes. So you get this. So functionals have the same property that functions do for differentials. So the action is defined as the time integral of the Lagrangian. And the Lagrangian is the function L, which is a function of some coordinate trajectory and then the rate of change of that coordinate trajectory, which we typically just rewrite as L Q and Q dot, and it's equal to the kinetic energy minus potential energy. So this is kinetic energy, and this is potential energy. So the action is defined as the time integral of the Lagrangian. So this actually should be a comma. So therefore, you have S, that's an integral. S is equal to the time integral from some initial time to some final time. So integral over time of the Lagrangian. Now, if we now consider the perturbation of the system, so we now look at the perturbation of this. So we want to find what condition must hold if this is equal to 0. So first we just expand this out. I'm going to copy this because I'm going to be pasting it quite a lot. So this is equal to L Q plus E and Q dot plus epsilon dot, so it's epsilon not E, then minus L Q Q dot. Keep working on this. This then becomes, by plugging in this definition right here, becomes L Q Q dot plus epsilon dl dq plus epsilon dot dl dq dot minus L Q Q dot. Shoot, did my AirPods not connect to this iPad this whole time? Well, hopefully the audio recording wasn't too bad up until this point. That is unfortunate. So let's continue. So obviously these two factors cancel out. So we get integral over time of this right here. And we can simplify even more. So this actually ends up being equal to get epsilon dl dq. Then we can put minus epsilon d dt dl dq dot plus d dt epsilon dl dq dot. So why can we do this? Because this might seem pretty ad hoc. Well, it's by using the product rule. So the fact that the total derivative of time of epsilon dl dq dot, move things this way, it's equal to the time derivative of dl or epsilon times just this, then plus epsilon change in time of this quantity. So what we did is this is in the equation already, which is this factor. So we just subtracted this over here. So we have that this is equal to this minus this. So we just plugged that in here. Now we can pull out an epsilon and then expand this. And this becomes epsilon times this time integral of dl dq minus d dt dl dq dot. Then you end up with a plus from initial time to final time d epsilon dl dq dot. And this term actually goes to 0. This goes to 0. Why does this go to 0? Well, what you're doing is you're taking the integral over time of the amount that the Lagrangian changes with respect to this. But the definition of having something infinitely close means that they must have the same beginning and end points. And so by the fundamental theorem of calculus, this value actually goes to 0. And so you're left only, or you're left with the condition that the path or the action is extremized if and only if this value here is equal to 0. And that value is only equal to 0 if the two values being subtracted are equal. Partial L, partial Q dot. So this is the derivation of the Euler-Lagrange equation. So the path is extremized if and only if these derivatives are satisfied. But then the next question is pretty obvious, like what is this? What's the interpretation of all of this? Well, recall what I said before in that QT, they're like coordinates. So these are generalized coordinates. And then this Q dot is, I'm going to just copy generalized. Oh, copy generalized velocity. And then this ends up being generalized force, which is actually written like this, the capital F. Um, and the reason for this is because in class or in physics, the traditional definition where you take the gradient of the potential and you get a force, well, the Lagrangian is like a generalized potential. So you have kinetic energy and potential energy. So when you're taking this derivative right here with respect to coordinates, it's like taking the gradient. And so it's like taking the gradient of a generalized potential with generalized coordinates. So it's a generalized force. And then this value right here, Q dot, this actually is generalized momentum. So the reason why you can think of this as such is because we have dl over dq. Okay, I don't want to rewrite everything. I'm just going to copy it. If my stupid pencil wouldn't. It feels like my iPad is just not working, doing everything I need it to do today. It's being weird. So this is the same thing because we can rewrite this generalized force like F. Then we end up with the time derivative of something here. Well, we know that forces are the time derivative of momentum. And so we have a generalized force as the time derivative of something. Well, then that just ends up being momentum. And actually a pretty neat example or a relation or is if you have kinetic energy equal to just 1/2 mv squared, we can relabel this v as q dot. So this implies that if we took the partial derivative of this kinetic energy with respect to q dot, like what is done here, then we get 2 times 1/2 m q dot, which is just equal to m, and then q dot squared, sorry, q dot dot, which is just generalized acceleration. So you just get something that looks like Newton's law. And so this is actually, I don't know if this is a term that's used but a lot, but I call it the generalized uh, Newton or Newton's second law. And so that's what Lagrangian mechanics pretty much are doing. They just generalize the Newtonian approach by looking at the efficiency of paths.